This video is the first on functions of several variables. Okay, so you've already looked at functions of one variable many times, and you're familiar with this even from school. So we're going to extend to functions of more than one variable. Okay, and first, the natural step is to look at a function of two variables. Okay, and then we'll generalize. And after we introduce the basic ideas, then we'll look at calculus in several variables. Okay, so multivariable calculus. Okay, all right, so let's start. A function of two variables. Okay, well, let's take the natural starting point. So a function of two variables. And let's call the variables x and y. Okay, is a rule okay, and the rule does the following. It takes the values of x and y, and these are specified, so the possible values that they can take are specified by what's called the domain of the function. Okay, and the rule does the following. It takes those two So it takes these two, it applies the rule, and we get a result that we call z. Okay, this is my z. Z with a little curly leg on it. Okay, so this is the rule, and frequently we'll call this just a function of x and y. Okay, so go back to school to your little function boxes. You take two numbers or a coordinate x, y, you apply some rule to it and you get out some z. And this f of x and y is often given by a formula. So for example, this function of x and y is just the square root of x squared plus y squared. Okay, that's nothing other than the length of a line, the length of a point from the origin, okay, in the xy plane. But it doesn't have to be given by a formula. It can be equally given by other means. So for example, let's have a function f of x and y, and it's defined by the following. It's 1 if x is greater than y, it's 0 if x equals y, and it's -1 if x is less than y. Okay? Okay, so it turns out that this function of two variables represents a surface. Okay, and in Cartesian coordinates, what we're saying is that, okay, so let's have an x, y, and z. Okay, let's have x and y. So we take some coordinate x, y. Okay, and there's a rule that gives us a value z. And here we can draw it as z being the value of the point, and it's the height above the xy plane. So for this coordinate xy, z equals this. Okay, and it's the height above the xy plane. So this is the value of z. Okay. So this is z for the point x and y. As you change x or change y, then z may change. Okay, and eventually you kind of map out a surface. Okay, so here's some surface. Okay, and all these points that lie on the surface are the values of z that correspond to the values of x and y. Okay, so for this x and y, z equals this number. Okay, the height above the plane represented by z. Okay, maybe we can make that a bit more concrete with an example. So let's think about an example. let's think about the curve. So z is a function of two variables, x and y. And in this case, let the function be the square root of a squared minus x squared minus y squared. Okay, and we need to define the domain of this function, so the values of x and y over which this is defined. Okay, the domain. And here we're going to use x squared plus y squared is less than or equal to a squared. Okay, so all the values of x and y that keep this thing under the square root positive. Okay, so the square root will be real. Okay, so this should be reminiscent of the equation of a circle. X squared plus y squared equals a squared. So here's our circle of radius a. In the x and y plane. Okay, and remember it has the equation x squared plus y squared equals a squared. Okay, so what we're saying is the domain is all the values of x and y that lie within this circle. Okay, so all these points. Okay, and this is a disk of radius a. Okay, that's what we mean by a disk. Okay, disk radius a. Okay, and it turns out that this function represents a dome. Okay, and we can see that if we draw the x and y and z. Okay, and we can consider different values of x and y and see what z they give. Okay, just like when you're drawing a function of one variable, x and y, so y equals some function of x. Okay, you choose values of x. Okay, and you can calculate the values of y according to this rule. So at this value of x, our function y equals f of x is here, 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 okay, and then you can connect the dots. So this is your function of x. Okay, so you choose values of x and find out what the value of the function is. Okay, here we can do the same thing. We just choose values of x and y, and we find out what our z is. Okay, so let's think about the case x equals y equals 0. Okay, so if x is 0 and y is 0, then z is just the square root of a squared, which is just a. So this implies that z equals a. So this is the point x equals 0, y equals 0, and it's telling us that z equals a. Okay, so we're at this point here. Okay, this is the point 0, 0, a. Okay, 0, 0, a. We can also consider all the points that satisfy x squared plus y squared equals a squared. Okay, and when x squared plus y squared equals a squared, then this thing vanishes, and we just have that z equals 0. Okay, so there's a group of points at z equals 0 that map out the equation of a circle in the xy plane, circle of radius a. Okay, this is a circle of radius a. Okay, at z equals 0. So this is x squared plus y squared equals a squared at z equals 0. Okay, and we can fill things in a little bit if we see that z squared equals a squared minus x squared minus y squared. So that means that x squared plus y squared plus z squared equals a squared. Okay, is our equation recast, but here z is positive. Okay, so we're only keeping z greater than or equal to 0 here. Okay, so if this is true, you can consider what happens when, let's say, y is 0. Okay, when y is 0, this means that x squared plus z squared equals a squared. So this is nothing other than the equation of a circle in the xz plane. Okay, so the xz plane has y equals 0 and it's a circle, semicircle of radius a. Okay, and if you set x equals 0, then you get a circle in the yz plane of radius a. Okay, and the yz plane is this one. Okay, so you see that you map out a dome. Okay, and it turns out that this is a hemisphere. Okay, so this is the equation of a hemisphere. This here, or we can have this. Okay, so, and you can see this here, x squared plus y squared plus z squared is nothing other than the length of a line in 3D. Okay, so if I have a coordinate system, let me draw here, x, y, and z. Okay, then the length of this line at coordinate x, y, z from the origin is nothing other than x squared plus y squared plus z squared, square rooted. Okay, so this is saying that x squared plus y squared plus z squared, so the length of this line is a constant. So you choose all the values of x and y, and therefore z, that this line is a constant. Okay, so here's something with a constant length, this pen. Okay, if I have a fixed origin, then all I do is change the x and y and z points so that the length remains constant. So basically I move this pen in any direction I choose, and the end point is a point on the surface. Okay, so you can see that this maps out a hemisphere. Okay, I can rotate in the circle. I can rotate like this, and that gives me these upper arcs. Okay, the circle gives me the lower circle that we saw first. Okay, so this is the points on a hemisphere. The points on a sphere don't have the z greater than or equal to 0. Okay, so a sphere is defined by x squared plus y squared plus z squared is a constant. Okay, and in that case you can go below the plane. Okay, so the end point of this pen lies on the surface of a sphere. Okay, let me clean this up. Okay, so we just saw the surface of a hemisphere. Okay, and we said that that was defined as a function of two variables, x and y, as the square root of a constant squared. Okay, a squared minus x squared minus y squared. Okay, where a is the radius of this dome. Okay, if we want the full sphere, then we also want, so we've got the dome. So we've got the dome. That's the z greater than 0 values. We will also want the bowl, okay, the z less than 0 hemisphere. Okay, so this is the z greater than 0 one, and the z less than 0 is just the same thing, but with a minus sign. Minus a squared minus x squared minus y squared. Okay, and they both have the same domain. X squared plus y squared is less than a squared. Okay, so the values of x and y are constrained to lie within a disk of radius a. Okay, so these two functions together give us a sphere. Okay, they define the surface of a sphere. Okay, and we can write that in different ways. We can see that this says that x squared plus y squared plus z squared equals a squared. Okay. And this is just saying that if we have x, y, and z, and we have some point x, y, z, then the length of this thing is a. Okay, and it's always a. So we move this about. So here we've got a fixed length pen, fixed at the origin. We move it about in all ways possible, and the end point of the pen is the value, is the coordinate x, y, z, and this lives on the surface of a sphere. Okay. We can also say the following. We can parameterize this using two angles. The first angle we're going to call theta, and that's the angle that this little vector makes with the z-axis. And then we're going to project this vector that goes from 0 to x, y, z onto the xy plane. Okay, so this is the xy point. Okay, so it has a value of x and a value of y. Okay, and if we look down from the top of the z-axis, then we see the xy plane, x, y, and we see the projection of this thing. Okay, and it looks like a straight line from the origin to the value of x and y, x, y, okay. And this makes an angle phi with the x-axis. So we're saying that this angle here is phi. Okay, so with those two angles, we can define our sphere as following. X equals a sine theta. And it's a sine theta because we're going to project onto the xy plane. Okay, so this is resolving this vector effectively, a sine theta. And then once we have this line, which corresponds in the xy plane to this thing, we now resolve this onto the x-axis. Okay, so this thing is a sine theta in length, and we resolve this onto the x-axis. So it's a sine theta cosine phi. Okay. Similarly, y equals a sine theta to get us onto the xy plane. Okay. And now we resolve this onto the y-axis. Okay, so this is a sine theta sine phi. Okay, sine phi. Okay, and then z equals, what does z equal? We just resolve this onto the z-axis, so it's just a cosine theta. Okay, and the sphere is defined by theta can go from 0 to pi. Oops. Okay, so theta can go from 0 to pi. Okay, either pointing up or pointing down. And phi can go from 0 all the way around to 2 pi. Okay, so phi can go all the way around the circle. Okay, to make a circle. And if you think about a circle, okay, if you rotate this from 0 to pi, this maps out the sphere. Okay, so this is the alternative definition of a sphere. Okay, and it's easy to see that these equations satisfy this. Okay, and I'll leave that as an exercise for you guys to do. So it's x squared plus y squared plus z squared, and you just use the fact that sine squared plus cosine squared is 1 twice, I guess. Okay, so this is easy to show. Okay, so we can go beyond thinking of functions of two variables. So for instance, consider the temperature in the room that you're sitting in. Okay, it depends on the x, y, and z coordinate. Okay, where you are in the room. Okay, so we can have a function of temperature that depends on 3 variables. And actually, if you turn your radiator on, so this is 3 variables. If you turn your radiator on, you may find that it changes over time. So you might have 4 variables. It also depends not just where you are, but also on the time. Okay, we're going to think generally, we're going to think about functions of n variables. Okay, and we're going to write each of the variables as x1, x2, x3, and so on, up to xn. Okay, so here, this is x1, this is x2, this is x3, and this is x4. Okay. Okay, so similarly to above, this thing just takes a collection from x1 to xn, okay, and assigns a rule, okay, to give us this thing, f of x1 to xn. Okay, and similarly to before, this thing could be defined in terms of a formula or in terms of by some other means. Okay. So let's finish this section by just thinking about a few more examples of the domains of functions. And it's important that we have a good understanding of this for the sections that come later on line integrals and surface and volume integrals. Okay, so we're looking at examples of domains. Okay, so let's think about a first example. The function z equals the square root of x plus y. Okay, and if you see a function written, so this is a function of 2 variables, if you see it written without a domain specified, then you assume that the domain is all the sensible values of x and y. Okay, so here we assume that z is a real, okay, x and y are real numbers, z is also a real number. Okay, so we're thinking of the domain being the values of x and y that satisfy x plus y greater than or equal to 0. Okay, so this square root stays real. Okay, so what does this mean? This means that y is greater than or equal to minus x. Okay, so how do we visualize that? Let's have our x and y axis. Okay, and the line y equals minus x is this thing, okay, going through 0. So this is the line y equals minus x. So the domain is telling us that y, the xy values are those that have y greater than minus x. So if this is the line y equals minus x, then y greater than that is everything above this line. So it's this region here, okay? So this function only considers, or is only defined in terms of x and y coordinates in this blue shaded region, okay, above the line y equals minus x. Okay, so let's think about a second example. Z equals log, natural log, of x minus y. Okay, and here we're saying that x minus y is greater than 0. Okay, so what does that mean? That means that x is greater than y, okay, or that y is less than x. Okay, so for this one, let's draw our axis, x and y. Okay, and we draw the line y equals x. Okay, so in this case, we have all the values of y that are less than x. So if this is y equals x, then the values of y less than x lie below this line. Okay, so this function z equals log of x minus y only takes coordinates from this region, okay, where the shaded this shaded area, the shaded section. Okay, let's think about a third example. Let's think about u equals the square root of x plus the square root of y plus the square root of z. And let's define the domain as x greater than or equal to 0, y greater than or equal to 0, and z greater than or equal to 0. Okay, and this lives in the first octant of your three-dimensional space. Okay, so let's have x, y, and z. Okay, so we're restricted to this octant here. So this is the zy plane, the zx plane, and the xy plane. Okay. So this is the first octant. Okay, extending to all x, all y, and all z greater than 0. First octant. Okay, so it'll be useful to be able to visualize these domains when we come to the later sections, especially the multiple integrals, line integrals, surface integrals, and volume integrals. Okay, so next we're going to think about limits, and that'll bring us nicely on to partial differentiation. So this is starting calculus in more than one variable.